This is a ferrite core. This is enamelled wire. You can make an inductor using these two things. Don't really know much about inductors, if I'm honest about it. In theory, with the coil, if I stick a wire through the coil, like so, I then inject an appropriate frequency signal through this wire that I'm wiggling, it will induce a current in the copper wire. Now, whether something as rough and ready as this will actually work is yet to be seen. In order to sense the signals from the inductor, I'm going to try using a comparator. This one's the LM393. Obviously I've got to solder it onto the board first, and then I will connect up the coil to the inputs, and there'll be a few resistors that are going to be added, and then we'll connect it all up to the scope. Right, I reckon they're all soldered. Whether that's destroyed the chip is a different matter, because there is some meltingness going on. I hope it hasn't. If it has, we'll just get another one out and try again. But I've got to tell you, soldering these very, very small components with my, shall we say, through-hole soldering iron is quite the challenge. I wonder if it still works. For want of better terminology, I'm going to call this a prototype. We have a little comparator there, a bunch of resistors taken straight from the application notes in the datasheet, which I'll put on the screen about now. You can see there's a 20 meg feedback resistor, negative feedback resistor there, which I can't imagine does a great deal of anything, to be honest. The signal comes in on the white and yellow wires, and the output is on the green wire, with the red and black being power. It's pretty much a standard sort of negative feedback amplifier. I suspect because the feedback resistor is such a high value, what I would expect to happen is for the signal to go high very, very quickly and max out at the voltage level of VCC. So if I stick a sine wave in through the white and yellow wires, I should get a square wave out of the green wire. I think that's how it's going to work. I think the best thing to do at this point is to try it and see what happens on the oscilloscope. the plan will be to use this resistor as a load on the signal generator, and I think it's a 200k resistor or something like that, and then pass this white wire through the coil like so, and then we can see whether we've got a signal on the white wire from the signal generator or not on the output by the shape of the output signal. I think that's how it's going to work. So when the prototype is connected up, and you can see that I've got a wire going through the middle of the coil. The wire going through the middle of the coil has a sine wave signal going through it, and then that is inducing a current in the coil, which is then going into the comparator, and the output of the comparator, which is this green wire here, is the blue trace on the scope. Should have plugged it into the green one, really, shouldn't I? We are indeed getting a signal out from the sine wave input. Now the sine wave is obviously an alternating current. I'm just going to drop it to a different profile. I'm going to put it onto a square wave and see if that makes any difference. With the square wave input, we're getting essentially twice the frequency of the output, and I'm going to assume that this is because the square wave isn't constantly changing, and there's periods when it's a flat signal, and that is when that's when current is no longer being induced in the coil. We'll try another wave pattern. So if we drop it down to a kind of a triangular wave, we can see that that too produces a square wave output. So we'll stick to sine wave for now. Actually, I'm going to put it on CMOS just out of idle curiosity. So if I'm driving the signal with essentially a digital clock signal, which is between 0 and 5 volts, we can see that the output is still essentially twice that of the input signal. And again, that's because of I think because of the flat top and bottom parts of the input signal. Just going to drop it back to sine wave for a moment because it looks prettier. Now the question becomes, what sort of output do I get if I disconnect the input signal altogether, so that there is no current flowing through that white wire you can see? And I'll just do that by disconnecting the load, like so, and we can see that we're getting exactly what we want to get, which is a very low signal on the blue output, and of course no signal on the yellow output. I would go so far to venture that this circuit works in the manner that I'd expected it to work. One thing to note with these LM393s is they actually contain two comparators, and I haven't used the comparator on this side of the board at all. So I think I am going to use that comparator, and I'm going to see if I can create a clock to drive the white wire going through the core, rather than relying on my signal generator. That might be interesting, mightn't it? So I've modified the comparator circuit to include a small oscillator, the purpose of which is to generate a clock signal, which I can then push through the ferrite core and pick up the output. Essentially, I'm making a clock. You can see the oscillator here, just here, and there's a capacitor and a big bunch of resistors essentially. Again, the circuit was taken straight from the application notes of the LM393, which I will put up on the screen here. And you can see the oscillator utilises a 100 kilohertz crystal, which was in the application notes, so all the values are straight out of the application notes as well. And now you can probably guess why I opted for a 100 kilohertz signal previously when testing the ferrite core. If I bring up the oscilloscope with this plugged in, we can see that we're getting a very clean square wave. So what I'm going to do now is I'm going to connect up the crocodile clips again through the core, the ferrite core, and see what the output's like, if indeed we get an output. So we can see now I've got the wire going through the coil, and the output on the blue trace at the top is, as previously, approximately twice the frequency as the clock signal, and that's to do with the way that the inductors induce current. It'll induce current on the rising edge of the square wave, and it'll induce current at the trailing edge of the square wave, but the flat bits are it drops off somewhat. If we can zoom in a little bit on the signal, let's try that. The only slight problem I can see really at this point is that the output voltage is basically about 3 volts by the looks of it, whereas the clock voltage is 5 volts. Such an output voltage may or may not be useful for driving logic circuits. I guess at some point we will find out. In any case, I think this probably works well enough for me to try and create a few more modules.